Hi everybody, this is lecture 27, the last lecture of our course, and today I'll do a course review geared towards our final exam next week. Alright, so let's get to it. So the first thing we talked about was double integrals. Right, when we do a double integral, we have two ingredients. One of the ingredients is a region of the xy plane. So here's a sample region, R, and then when we set it up, so the double integral of a function over of x and y over R, the way we set it up is we find the minimum value and the maximum value of x and of y in the whole picture. And then we do an iterated integral from with respect to dx from this minimum value to this maximum value of x. And then for each intermediate value of x, we do a vertical integral going up with respect to y, which goes from a certain minimum value of y to a maximum value of y. But these minimum and maximum values, they depend on the x that you fixed. Okay, so you get so the inside integral here, the bounds for the inside integral, this y min and y max, they depend on the x you fixed. If I had fixed this other x, then y min and y max would be different. And then you just plug in the function, then write dy and dx. So the point is that you do two single integrals of functions of a single variable. Here on the inside integral, you're fixing an x value between x min and x max, and then you're doing that. The picture is that we're swiping the region vertically like this. Okay, so when we compute, so that's the first topic we talk about. The next topic was polar coordinates. These are very useful when we compute double integrals, coordinates. Right, so the picture is that instead of using two numbers, so we're still using two numbers to describe points in the plane, but instead of using the distances from the two axes, x and y, we're actually using the distance from the origin and the angle theta measured from the x-axis towards the y-axis. So x in terms of the new coordinates, in terms of polar coordinates, is r times cosine theta, right? It's this part over here. And y is r sine theta. And crucially, so when we use this, when we integrate with polar coordinates, the very important part is to remember that dA is r times dr, d theta. We usually set up the integral with d theta outside, so we find the minimum value of theta in the whole region, then you increase the maximum value of theta in the whole region, so you place your region in a cone like this, and then for each intermediate value of theta, you shoot out a ray, and the r integral, the bounds for the r integral are the moment when you first enter the region, the value of r when you first enter the region, and then the upper bound for r is the value of r when you leave the region. Okay, so let me. So here's something, a very important skill, and that's to be able to describe familiar shapes in terms of new coordinates. So for example, if we have, let's say we have a circle, here's basically the most complicated example we've seen when we were working with polar coordinates. So how do we describe a circle that's not around the origin? So the origin is in the boundary of the circle, but the circle itself is not around the origin, right? So So let's say this is 1, this is 2. We're talking about a circle of radius 1, but centered around the point 1, 0. So the bound. Let's talk about the bounds in this case. Right. So this circle has equation x minus 1. It's just a standard circle, but it's centered around the point 1, 0. It's shifted to the right by 1 unit. So the equation for the circle is x minus 1 squared plus y squared equals 1. So if I want to find if I wanted to integrate over this region, I would first convert the equation. So I need to figure out. So I can. Okay, so on this region, the first part is that theta would go from minus pi over 2 to plus pi over 2. So that part is clear. So minus pi over 2. So theta is between minus pi over 2 and pi over 2. But r, the trick is if you fix an intermediate value of r, now if you fix a theta, you shoot out a ray, you enter the region immediately. So r starts at 0, but it stops here. But the point is I need to figure out what r is at this point. Right? So I need to know what, so the r coordinate of this point depends on theta. So I need to know what r is given theta on the circle. Here I have an equation that relates x and y on the circle. To get what r is over here, I'm going to convert this equation to polar coordinates. So let's do it. So I get, so first let me just massage the left hand, massage this a little bit. So we get x squared minus 2x plus 1 plus y squared equals 1, which is the same as saying that x squared plus y squared equals 2x, right? I canceled the 1 and moved the 2x to the other side. Now I can convert this to polar coordinates. The same equation in polar coordinates reads r squared, x squared plus y squared is r squared, equals 2x, x is r cosine theta. And then this tells me that for every point except at the origin, so this tells me that at every point except at the origin, r is equal to 2 cosine theta on this circle. So on the circle, r is equal to 2 cosine theta everywhere except at the origin. And at the origin, this equation doesn't really make sense because theta is not defined at the origin. The origin doesn't have a theta coordinate, a well-defined theta coordinate. Okay, so this is what r is at the circle, and when I shoot out this ray, I leave exactly when r touches the circle, so I'm going to stop r. The upper bound for r is 2 cosine theta in this case. All right, so that's it for polar coordinates. The next thing we talked about was general changes of coordinates. Right, so before here I expressed x and y in terms of r and theta, and I told you that dx dy is r times dr d theta. So we learned about the Jacobian determinant. That tells us, so if I have x and y expressed in terms of two other coordinates u and v, then a very important thing that we learned is that dx times dy is the absolute value of the Jacobian determinant. That's of x and y with respect to u and v, multiplied by du dv. So you can change coordinates to u and v in the integrals as long as you do this substitution. And of course the Jacobian determinant is given by the following formula. It is the determinant of the matrix of derivatives of x and y with respect to u and v. So first the two coordinates of x and then the two coordinates of y. Sorry, the two partials of x and the two partials of y. Right here, where I'm assuming that x and y are functions of u and v. All right, so this is a good review of double integrals. Let's move on to triple integrals. So that was an interesting topic. So when we do so triple integrals take place over solid regions of three-dimensional space. Let me draw a solid region here in 3D space and make a few remarks. Tell you how we can set up an integral in 3D. Right, so here's our solid region. And here is the projection of said region onto the xy plane. Okay, so E is our solid region and R is its projection. R is going to be important. It's the way it's going to be useful for when we set up the triple integral. So to set up the triple integral of a function f of x, y, z over E, we can do this with Fubini's theorem for triple integrals. This says that I can set it up by doing a double integral over the projection, over R. And then for each point in the projection, okay, so I'm going to do a double integral over the projection. Let me just say it's going to be a double integral over R, and say in the order dy dx or dx dy, it doesn't matter. And then for each value, for each point in the xy plane, I'm going to do a vertical integral with respect to dz, where z increases from some minimum value that depends on that x and y to some maximum value that depends on x and y. So here I'm assuming that the region is nice to integrate over. So this means that it satisfies the vertical line test. It's nice to, here I'm assuming that it's nice, this region can be nicely integrated in the orders dz dy dx or dx dy, dz dx dy. So with dz first, meaning that it satisfies the vertical line test, right? But then you get an inside integral from some minimum value that depends on x and y to that max. And then you integrate the function. Here I'm going to hide the dependency of the function on x, y, and z, and then you get this. Right, but the point is, you're doing a double integral over the base, and then for each point in the base, for each point in the projection, you go up vertically along a line segment, and in the z direction, and the bounds are the moment when. So for that fixed, the bounds are the endpoints of this vertical line segment. Okay. So, but this is not our only way to view triple integrals. Sometimes it's useful to work with them in a slightly different way, having the dz, so thinking, instead of thinking in terms of the projection, and by the way, the projection of the region is the set of all points in the xy plane that you get by forgetting about the z-coordinate of points in E. For example, if I take this point and forget about its z-coordinate, I get a point over here. Take this point, forget about the z-coordinate, I get a point over here. And then the projection is all points you get in this way. But there are two ways to think about triple integrals. The other, so the other one, so this is in terms of the projection. The other way to think about triple integrals is using, by slicing the region, right? So the other way, for example, here, I could say, so you can do these things not just with the projection onto the xy plane. You could also do it with projections onto the xz plane or yz plane. But here I chose xy plane. I could also work with slices. So for example, I could work over I could just look at the minimum and maximum values of the x coordinate on the whole region. So that's the same as the minimum and maximum x coordinates in the projection, because the points, the x and y points, the points x comma y that you get in the projection come from points in the region. So you look at those, and then you set up a single integral with respect to dx from x min to x max. These are the minimum and maxima of x in the whole 3D shape. And then for an intermediate value of x, So this cuts my region below like this. I would look at the x slice. So if I fix x, I'm going to cut my region horizontally like this. And then I get a slice, a vertical slice like that. Right, this is the x slice. It's what you get by intersecting my region with a copy of the YZ plane with x fixed. And then you do a double integral over the x slice, in blue, of f. Then over the x slice, the coordinates are y and z, dx. So the point here is that you can, basically there are two ways you can group the integrals. A double integral that followed by a single one, or a single integral followed by a double integral. And these both of course are compatible, right? If I set up this double integral as an iterated integral and do the same for this one, I'm going to get exactly the same bounds for the three single integrals. Okay, but this is to stress we have two useful ways to think about set up triple integrals. Either with slices. These here I use x slices. I could also use z slices, which would look like that, or in terms of the projection onto one of the planes. So another very useful thing to do when computing triple integrals is to use coordinate systems that are specialized to the problem at hand. Namely, in these the ones we learned about, we studied in detail, were cylindrical and spherical coordinates. So here are the cylindrical coordinates. They're basically polar coordinates with z included. So just replace x and y, but then keep z. Right. So if I have a point here in three-dimensional space, the coordinates of the point will be the height, and then the distance from the z-axis and the angle around the z-axis. The distance from the z-axis is r, and the angle around the z-axis is theta. So x is, in this case, r times cosine theta, y is r sine theta, and z is just z. And of course, and the volume element, dv, is r dr d theta dz. Or maybe you want to put dz in front, but usually want dr and d theta in this order. So we learned about cylindrical and we learned about spherical coordinates. So the way spherical coordinates work is this. Okay, I want my pictures looking minimally decent. So the way spherical coordinates work is if I give you a point, the coordinates for that point are the distance from the origin, that's called rho, the angle phi from the z-axis, that's measured from the z-axis towards the ray mapping to the point, and then finally the last of the spherical coordinates is the angle of the point around the z-axis. So we have an angle from the z-axis that's like latitude in geography, and we have in cartography, and we have an angle around the z-axis that's like longitude. Latitude and longitude in cartography. Except that the conventions are different, right? So in cartography, phi would be measured coming like that, with being 0 at the equator. With our conventions at the equator, phi is equal to pi over 2. Now to remember our formulas for the coordinates, so the easy one is z. So z is just phi times cosine, rho times cosine phi. And then we have x and y. So x and y are r times cosine theta, and then times sine theta, right? So this is r times cosine theta and times sine theta. Now, so r, this distance over here is rho sine phi. Then multiplied by cosine theta, I get x. And r again is rho sine phi. If I multiply by sine theta, I get y. And the volume element in spherical coordinates is, going to write it down here, the volume element in spherical coordinates is rho squared sine phi d rho d phi d theta. And again, this is the order we usually want to place these differentials in. All right, so that's the stuff, that's the material we covered before the first midterm. Now let's move to the stuff we covered after the first midterm. The first topic was the chain rule. The chain rule is pretty straightforward. So we want to use it when we have a function that depends on two variables or three, but let's focus on a definite case here. So we have a function that depends on two variables, and each of the variables depend on a third parameter. Okay, so f depends on x and y in turn depend on t. And then I ask you, how does f depend on t? So what's the rate of change of f with respect to t? And the answer, and the chain rule just tells me, it just gives me the answer. It just tells me that this is the x partial of f multiplied by dx dt plus the y partial so there's plus a contribution that comes from the y partial, so the first term depends on how f changes with x, and then you multiply by how fast x is changing with t, and then there's the second contribution coming from how f changes with y multiplied by how y changes with t. I should note here that so this is the short way to write down the formula, so put it in a box, but I should note that when we apply this, normally we have to be a little bit more careful. So really what we're doing is d dt of the function f of x of t. Right, can I do this? Oh, okay, let me just say that r of t is x of t, comma y of t. Okay, then we want to know d dt of r of t. Right, and what's going on here? So this answer is going to be df dx evaluated at this point r of t at x comma y multiplied by dx dt. Now x just depends on t, it doesn't depend on a position in space, so dx dt is evaluated at t, and then plus a contribution with respect to y. So here I'm just rewriting the same formula but telling you where to evaluate the various functions, because this is the sort of thing that people usually mess up in exams and homework. So the point is the functions with respect to x and y we have to evaluate at points of the xy plane, and the functions of t we evaluate at points of values of the parameter t. So here we there is I can also write this as the gradient of f evaluated at the point x r of t, and then you do multiply it. I mean, this is the dot product with the velocity, with dx dt comma dy dt, right? If I do this and evaluate it at t. So here I'm using the gradient vector. Right, which is pretty clear. So the gradient of a function of two variables is just the vector with the two partials of the functions. A function of three variables, the gradient of a function of three variables is just a vector field whose components are the three partials of the function. So a very major thing we learned about the gradient is that it's always perpendicular to the level sets. Right, so if I look at the set of all points, so let's say this is the set of all points where f is equal to 1. So if I give you any point, f is going to be, f can have, here what I'm doing is I'm grouping together, so the level sets are the sets you get by grouping together points in the xy plane where f has a given value. Oops, so these two sets are disjoint. So this is the set where f is equal to 1, the other one is where f is equal to 2. And then the big theorem, the cool thing we learned about the gradient, the geometric interpretation of it, is that the gradient is always perpendicular to the level sets. So if I evaluate the gradient at this particular point, and assuming that, so for this point, when I say this point lives on the curve where f equal to 1, this means that f at that point is 1. Well, so if I take a point and compute its gradient, then the gradient is perpendicular to the level set, or more precisely, perpendicular to the tangent line of the level set at that point. So we also learned about directional derivatives. Oh, well, let me just hold that thought for a second. So the gradient is perpendicular to level sets, and also it tells you, so it points in the direction where the function increases. So you see, so here it's pointing towards level sets, for larger values. So we talk about directional derivatives. So if I have a unit vector, a direction, u hat, so this is a unit vector, the directional derivative du hat f, this is a function, but if I evaluate it at a particular point, it tells me tells me the rate of change of f in this direction u. So it tells me what happens if I go 1 unit. So for each unit in the direction of u that I move, for each unit that I move in the direction of u, by how many units does f change? This is the directional derivative. So the main thing from a computational standpoint, the main thing to remember is that this is just equal to the gradient vector multiplied by u. So this is just picking up the projection. When you do the dot product, it's just picking up this component over here. It's picking up the projection of f in the direction of u. So this number is largest when u is just in the same direction as f. So the direction of the gradient is the direction where f increases the fastest. And it's 0, so if u is tangent to the level set, then the dot product will be 0. And the function won't be changing, the derivative won't be changing, and that's consistent with, being tangent means you stay at the level set to first order. Okay, so that's it for derivatives. Let's move on to integrals. So we talked about work and line integrals. Okay, so we're going to be integrating functions, vector fields in 3D, let's say. Let's move up from 2 to 3 dimensions. So the work that a vector field, so P, Q, and R are functions of x, y, and z. The work that a vector field f, this vector field f, does along a curve with an orientation c, is denoted by this, like this. And we usually set this up using coordinates. So f has components p, q, and r. And dr is, so it's this differential along the curve. Let's say our curve is down here. It has an orientation. So dr is this infinitesimal vector. So delta r. So when we integrate, we're breaking up the curve into a bunch of pieces, And dr is this vector that points from one little piece to the next. So it depends on the orientation. If you change the orientation of the curve, then which piece comes before and which piece comes after, that changes, and then dr changes its sign. But anyway, dr has components delta x and delta y, delta z. So the infinitesimal version has components dx, dy, and dz. So if we work out this dot product, we get the integral over c, and that's the same way to write a different way to write the same integral. We get the integral of p dx plus q dy plus r dz over the curve. These are two ways of writing the same line integral, one with vector notation, one with component notation. We evaluate both using a parametrization. So let's say r is our parametrization. So this gives us x, y, and z in terms of a single parameter t along this curve. So t is between two numbers a and b. And then if we have a parametrization, so if you give me t, then r of t is going to be a point on this curve. So so when t is a, r of t is here. So r of a is here, r of b is here, and for an intermediate value, r of t is in the middle. And as t increases, r of t traverses the curve. That's what a parametrization is. So using a parametrization, we can set up the integral like this. We just replace our curve with the interval for the parametrization, the domain of the parametrization, and then we evaluate our vector field at the corresponding point of space corresponding to a parameter value. Then you multiply that by dr dt multiplied by dt. So if you omit the points where you're supposed to evaluate the functions, this is just like replacing dr with dr dt times dt. Now, there's another way to write dr, and that's the unit tangent of the curve multiplied by ds, the arc length element on the curve. So the unit tangent at any point just looks like this. It's a unit vector. So it's a way to build this unit vector is you take the velocity and then you divide, which is tangent to the curve, but it's not a unit vector, and then I divide by its length. That gives me the unit tangent. And ds, the arc length element, that's distance on the curve. If we think that this curve is the trajectory of a particle whose position at time t is r of t, then you see that the distance is, it starts to make sense that distance is speed, so ds, the length is speed times time a time interval. So we could also have a t times ds instead of this, and would still be the same integral. Okay, so that's it for work in line integrals. Let's talk about flux and surface integrals. That's a more recent topic, but it's very, very similar. Okay, so let's say, so here's our surface. It's curved, lives in space, and here's its normal vector. Unit normal, so you get one for each point on the curve on the surface. Oops. And we still have our vector field PQR from before. And then the flux of this vector field through the surface, that's the same as, so ds is the same as, let me just write the whole integral again, but all I'm changing is ds. So that's the same as a double integral over s of f dot ds written out in full. So that's the unit normal multiplied by the area element on the surface. So this integral is, so if we have a parametrization of the surface, so here I'm going to give you a formula for points on the surface in terms of two parameters. To cover a surface, I need two parameters. So r of uv will be a point on the surface. As uv changes, this point moves around and covers the surface. So here's our parametrization. And u and v, they are constrained to some domain, right? So there are ranges. So d tells you the bounds for u and v. So if I have a parametrization like this, then I can set up my double integral as a double integral over the uv plane, over this region D, the domain of the parametrization, and then you write out the function, the vector field in terms of u and v, and then ds is just the cross product of the two partials of the parametrization, or I should say plus or minus that, multiplied by du. Oops, here the second parameter is v, not y. Multiplied by du dv. Okay, so what's going on here is that the unit normal, so we worked this out, right? The unit normal, so so the partials are derivatives you get by fixing one of the parameters. So if you fix one of the parameters and let the other one vary, here, so if instead of doing all this, if I fix one of the parameters, I'm just going to get a curve like that. Differentiated, I get a tangent vector. If I do the other partial, I get a different tangent vector. If I do the cross product of those two vectors, I get a vector that's perpendicular to the surface. And then if I divide by its length, I get a unit normal. I get a normal vector of length 1 that's perpendicular to the surface. Now, this may or may not be the unit normal that I'm using to compute the flux, that I chose to give, to specify the sign of the flux at the end. Right, so, but in any case, this gives me a bunch of unit vectors, which could maybe be minus the one I'm interested in, but that's the furthest away it can be from the one I'm interested in. So n is this quotient, ds, the area element on the surface, on the other hand, oops, without the arrow, it's the length of that cross product times du dv. And so when you multiply n times ds, you get something that's easier to compute than ds because there's one fewer step. You don't have to take the absolute value, but on the other hand, you still have to decide a sign. So the most common case is that of a graph. So let me at least give you an idea of what, just to put together here what happens in that case. So here our surface S is just given by the equation z equals a certain function of x and y. So in this situation, the cross product of the two partials. So here parametrization is we parameterize points on this graph using x and y. Right, and then z is just f of x, y. The cross product of the two partials, of the parametrization, is minus f sub x minus f sub y, 1. And so, ds, so ds without the arrow on top of it is the length of this cross product. That's the square root of f sub x squared plus f sub y squared plus 1 times dx dy. And the unit normal is just, it's plus or minus this divided by this square root. And then if you want to decide whether it's plus, so the decision is, so should we use plus or minus? Well, the answer is, what orientation are we talking about? So did the problem ask you for the upward flux? Did it want So if the vector field is going up like this, do you want the flux to be positive in this case? Are we saying we're giving the surface the upward orientation? In that case, the normals should be pointing up. And if I want normals to be pointing up, I want the third component of the normals to be positive, so in that case I use a plus. Otherwise, but if instead I want normals to be pointing down, then I should use a minus sign. So this depends. The point is here, S, it's hidden, but when you do a flux line integral, the choice of the orientation is part of the data, is part of the input before you compute the integral, and that input determines this sign. Okay, so we know about line integrals, we know about surface integrals. Now I'd like to tell you a bunch of results that connect line integrals and surface integrals. And these are the big results of our class. So, but before I do that, let me just tell you about some derivatives, right? These results tell you what happens when you integrate a derivative, all of them. So here are the special derivatives of vector fields that we learned about. So divergence and curl. So let's say we have a vector field F with components P, Q, and R as before. Then the divergence of F has this formula. It's a function. You get it by taking the x partial of the first component plus the y partial of the second plus the z partial of the third. And a good way to remember this is to imagine that you're doing the dot product of the gradient. So here we have a fake vector whose components are ddx, ddy, ddz. I say fake because these things are not numbers, so I'm not sure what to make of a vector whose components are not numbers, but for the purpose of remembering what the divergence is, you can just think that you're doing the dot product of this with the vector field PQR. The other kind of derivative we learned about is the curl of the vector field, which has a wild formula. So it's the x component does not involve p nor x derivative. It's just r sub y minus q sub z. The second derivative does not involve q nor y. It's I guess p sub z. I'm cheating. I'm looking at my phone here. So it's p sub z minus r sub x. And the last component, that's the familiar one. It's q sub x minus p sub y. So this is the curl. And the way to remember this formula is to work out a cross product between the gradient vector that I wrote below and a vector field. If you just work out this cross product, you're going to get this every single time. Okay, so these are our derivatives, or special derivatives of vector fields. And now let's talk about theorems that tell us, these theorems that tell us what happens when you integrate a derivative. So the first theorem is the fundamental theorem of calculus. So FTC for line integrals. So this one, so each of these theorems comes with a picture. So this one says this: suppose you have a curve that connects two points A and B. Then the integral over this curve of the gradient of the vector field, of this function, of a function. So I'm sorry, I'm integrating a vector field, and namely the gradient of some function. So if I integrate the gradient of a function along a curve with respect to dr, the result is just the difference between the values of the function at the two endpoints of the curve. So this is the first big theorem we learned about. It tells you what happens when you integrate the gradient of a function, the derivative of a function. And it's almost as if the derivative cancels with the integral. And then the curve is replaced by its endpoints, by its boundary points. All right, our next result is Green's theorem. So here's the picture that comes with Green's theorem. So we have a closed curve in the xy plane. So it's a closed curve with the positive orientation. And R is the region inside this curve. Right, what the theorem tells us is that if you do the integral around C, and here it's line integral and the curve is closed, I'll even denote it with, I'll put a circle in there to indicate that the curve is closed, that the theorem only applies when you have a closed curve. So if you do a line integral over closed curve of a vector field with components P and Q, here I'm writing the line integral using component notation, then that the result of that integral is just equal to a double integral in the region inside the curve of a function, and the function is is constructed with the derivatives of the vector field of P and Q, right? So this is the curl of the vector field whose components are P and Q. So that's our second big theorem, Green's theorem. So again, look what's happening. We had a region. So if you read it this way, it's exactly the same as this formula. So here I replaced, I canceled a derivative with an integral and replaced the curve by its boundary points. And if you read the Green's theorem this way, I'm canceling this funny combination of derivatives with one of the integrals and replacing, so then you're left with P and Q by themselves and replacing the region R with its boundary curve. I should note that R could have multiple components, right? If it had a hole in here, then the boundary curve of R would be this. Sorry, if R had a hole, right? If R looked like this, then you would have something like that. Actually, the orientations would be like this. Okay. So that's Green's theorem, our second big theorem. The next big theorem, which is the grown-up version of Green's theorem, is Stokes. You'll see the similarity is uncanny. I mean, for good reason. Stokes' theorem is a generalization of Green's theorem. So Stokes' theorem says that if you have a region in three-dimensional space, not a region, a surface. Let me just draw it like a surface. So that's my surface S, and let's say so we're going to be doing here. C is the boundary curve of S. Oh no. So C is the boundary curve of S. And also we're going to give, so we have to give the surface and the curve compatible orientations in the sense that we spent a great deal of time discussing. Right, so I need to choose, so if I look at my surface from above toward the normal, then I should see the curve going in the counterclockwise sense. So this is the situation, and Stokes' theorem tells us what happens when you do a line integral around this closed curve in space. So if I do a line integral around the boundary of a surface S, that's the same as doing the double integral, the surface integral, as computing the flux across the surface of the curl of the vector field. Here, the curl in 3D is a vector field, and then I can do so ds. I should recall. It's always good to recall ds is the same as n times ds without the arrow. So here I have a vector. So the curl of a vector field is another vector field. Here I'm integrating that other vector field through the surface. Again, the derivative cancels with one of the integrals. I mean, morally, the derivative cancels with one of the integrals, and I'm replacing the region of integration, in this case a surface, with its boundary curve. So that's Stokes' theorem. The difference between Stokes and Green's is that this region here can be lifted. It doesn't have to be contained in the xy plane. You can lift it and have it be floating around in 3D space. Okay, so the last big theorem of the class is the divergence theorem. So here, now we're going up one dimension from, so let's put these things in, let's look at the dimensions of these theorems. So here we're integrating over a curve that's dimension 1. In these two theorems, we're integrating over a surface which has dimension 2, and the flat region of the xy plane is an example of a surface. It's just a flat surface that happens to live in the xy plane. Really, you should think that Green's is a subcase of Stokes. And then there are only 3 big theorems: the FTC in dimension 1, Stokes in dimension 2, and now the divergence theorem in dimension 3. So Stokes' theorem concerns a closed surface in 3-dimensional space. So that's our surface S. And it also concerns the region, the solid region bound by this surface. And for the theorem to apply, we have to equip the surface with the outward unit normal. Right, so we're using the outward unit normal on this surface. And so the divergence theorem applies when we're looking at the surface, the flux of a vector field through a closed surface. So we're looking at the flux of a vector field through a closed surface. Okay, so the first thing that people could think, so here's our vector field. So one thing that you could think is that the flux through a closed surface is always going to be 0, because whatever flows into the surface ends up leaving the surface afterwards. That's not quite true, because the vector field could have divergence, could be expanding, diverging inside this surface. So the theorem tells us that what I just told you, that whatever comes in also comes out, that happens exactly when the vector field has, well, not exactly, but that happens when the vector field has divergence 0, but not in general. So the theorem tells me that the flux of a vector field through a closed surface is equal to the triple integral in the region inside that closed surface of this function, the divergence of the vector field. Let me write divergence with gradient notation. Right, so this is a function, and you integrate it over this solid region, you get the same as the flux of the vector field through the solid region. Once more, it's as if one of the integrals cancels with one of the derivative, and the price you pay for that is that you replace the solid region with its boundary surface. So that's the last big theorem that we covered in our class. So to conclude this review, I'd like to touch on one last topic, and that's of conservative vector fields. Just make a few remarks about them on this side. So conservative fields. So these are our vector fields. So a vector field, but the definition I give you for conservative is a vector field with the property that whenever you integrate it around a closed loop, you always get 0. So this is the same, but we later learn that that's the same as saying that the vector field is the gradient of a function. So a vector field is conservative. So this is the same as gradient fields. Okay, so we learned about a test for conservative fields. The test is that if okay, so there are two conditions. So if the curl of f is 0, so in 2D, this means that qx is equal to p sub y. And in 3D, this is really three conditions. Right, there's qx equals q sub y, but there is also maybe, I think it's r sub x equals p sub z, and another one, I mean, there are three conditions in 3D. It's just the three components of the curl have to be 0. So the first condition for a conservative vector field is that if the curl is 0, is that the curl for, so if I have a vector field, it's going to be conservative. I know it's going to be conservative if 1, the curl is 0, and 2, the vector field is defined on all of space. R2 or R3, depending on in 2D or 3D. All of, in 2D, R2, and in 3D, all of R3, all of space. Then, in this case, I know that f is the gradient. The vector field is the gradient of a function. Right, so this is the test we learned for conservative fields, and we also learned that even if I give you any vector field f, and if it fails the first condition, if the curl is not 0, then you know for a fact that it's not the gradient of any function. And I'm not going to do this now, but I do encourage you to experiment, to remember, to remind yourself what you do after this. So once you know that f is the gradient of a function, how do you find that function? This is a good exercise that I recommend you guys to do. Okay, so this concludes our this course review, and also concludes sadly the last lecture of this course. I was very happy to teach it to you guys. So thank you so much for listening, and I'll see you around. Bye-bye.